Welcome my friends, welcome to my next lecture. So this lecture I will talk about some change of variables in triple integrals. First of all, I will start with some properties of triple integrals. In my last lecture I talked about how I can define triple integrals. That means if I have a function say from some rectangular cube in R3 to R real valued functions, then I have defined what is the meaning of what is called Riemann-Darboux integral in that setting, and that I am saying in particular since I am in 3 dimension, this is triple integral. So I have defined. So there are couple of ways you can define. So I have defined like in terms of Riemann sum, okay, and also upper integral and lower integral, or upper sum and lower sum, in that also you can also define. Now in this lecture I will talk about some properties of triple integral, and then I will talk about couple of simple domains. There I will show you that how you calculate your triple integral in terms of say iterated integral, and some couple of applications I will give if time permits. Okay, so as I said, I think I should start with some properties of triple integrals. So definition of triple integrals I have defined in my last lecture as a Riemann sum, and then you see the whatever properties of double integral in the setting of from functions or scalar field from R2 to R, there whatever properties we have seen in the context of double integral, similar sort of properties also true in the context of triple integral. Let us see what are the properties. Okay, so these are the, okay, so this is actually, there is a typo, properties of it should be triple integrals. Okay. Okay. So what are the properties? So like suppose if I start with a function f, suppose which is triple integrable. Now if I hit it with some constant kf, k times f, where k is a constant, what will happen? K will come outside from the integral. So that is same as, that means integration or triple integral of k times f. This is dv. dv actually you can also write like dx, dy, dz. So whatever, anyway, either you can write dv or dx, dy, dz. So thing is that if I have a functions f which is triple integrable, if I multiply that functions by a scalar, that means kf is a new integrable functions if I hit it by scalar. So integration of kf over domain d dv, which is same as k will come outside times of triple integral of f dv. That is for every scalar. Okay, there is another typo, this should be k. Okay. Second one, this is the first one. Second one is that if I have two triple integrable functions, that means f and g, if I take the sum, this is also triple integrable, okay, and that sum will distribute like this same as integration triple integral over f plus triple integral over g. So that means if I have f plus g, triple integral over f plus g, which is same as triple integral over f, triple integral of f plus triple integral of g over the domain d. What about the third one? Third one is kind of if f of x is dominated by the function g of x, and suppose f and g both are triple integrable, then what will happen? Integration triple integral of f dv over the domain d, which is also dominated by triple integral of g over the domain d. Now another one is that if d is subdivided into two simple regions, say d1 union d2, with a caution that note that the only overlap between them will be a common portions of boundary cup. If this is the case, then the full integral triple integral of f over this domain d, which you can distribute over d1 as well as over d2. So that means integral over f or integral of f over the domain d, which is exactly equal to integral of f over d1 plus integral of f over d2. Another one, if modulus of a function's f is Riemann integrable or triple integrable, then you have this kind of estimate. That means you can show that f is also triple integrable. Not only that, if I take the absolute of my values which is dominated by integration of the absolute, that means you can push your absolute inside the integrand, that is what it says. So this kind of estimation true provided modulus of f is Riemann integrable. So if modulus of f is triple integrable, then f is triple integrable, and integration of f over d, if I take the absolute which is dominated by triple integral of modulus of f, that means you can push your absolute inside the integrand. And this is the kind of application. So if I just integrate the constant function 1 over the domain d, which will give you the volume of your domain d. Okay. So, this like if I have a like if I give you some domain D and I say that okay, calculate the volume. So, this is kind of application you will see. You have to integrate the constant function 1 over this domain, and whatever you will get, that will give you the volume of your domain D. Okay. So, this is actually kind of Fubini's theorem. It says that triple integral of f over a bounded region D in R3. Okay. What it says is the following. So, first of all, I am just writing as a theorem. So, it says that let a D be a bounded region in R3, let f be a scalar valued bounded functions on your domain D. Now, if f is a continuous function, now you just think about the similar sort of theorem in the context of double integral. There also I have assumed that if my function is continuous, then the corresponding function is Riemann Darboux integrable or double integrable. Not only that, the iterated integral also exists, and the value of the double integral is exactly equal to the both iterated integral. So, similar sort of kind of things also true in the context of triple integral. So, if f is continuous on your domain D, then f is Riemann integrable or f is triple integrable. Not only that, Fubini's theorem holds, that means the iterated integral exists and equal to your triple integral. Now, what is iterated integral? If I recall in the context of like double integral, if you remember, so if I have a functions from f, say some domain D subset of R2 to R, if you remember, so iterated integral means what? So, this is the function, right? X goes xy goes to f of xy, right? This is the function. So, if you remember, I consider that keep y is fixed, think about is a function of only x variable. So, if I keep y is fixed, think about is a function of x variable, perform integration, then it will give you. So, like for example, if you remember, suppose if I have a function, just I am recalling. So, if I have a function say from AB cross CD, which is subset of R2 to R, and suppose your function is continuous function. So, then what is the iterated integral? If you remember, so this is corresponding x variable, this is y variable. Okay. So, that means iterated integral, if you remember, a to b, c to d, like f of x y. So, first I am saying that keeping x variable fixed, I am integrating with respect to y variable, and then I am integrating with respect to x variable. So, therefore, what I am doing is that I have a function f which is a continuous function, then I am first integrating over y variable keeping x fixed. So, therefore, if I fix x and if I think about is a function of y goes to f of xy, so that means this kind of functions, if I think about for fixed x, I am thinking this is a functions, and if I assume that f is continuous function, this is also a continuous functions over the interval c to d, which is subset of R to R, okay. Then it is Riemann integrable. You perform the integration, then it will give you some value, and that value depends on x, because for each fixed x, it will give you, the integration will give you some value. So, that means that c to d f of xy dy, it will give you some value and which depends on x. So, that means I can write it say capital A suffix x. Okay. So, now finally what you consider x from a to b to a of x. This is the function which is again it is a point in R. Now, if this function is, so that means what? That means I am keeping x is fixed, that means I am integrating over c to d with respect to y variable, it will give you a function of x, and then I am integrating with respect to x. So, that is called iterated integral. So, that means first keep x variable fixed, perform the integration with respect to y variable, it will give you a function of x, and then you perform the integration with respect to x variable. That will give you one iterated integral. Another iterated integral, you have c to d, a to b, f of x y. Then what you have to do? First you have to perform with respect to x variable and then y variable. So, that is called iterated integral. So, and if you remember, the Fubini's theorem says if my function is continuous, both the iterated integral exists and the double integral exists, and they are all equal. So, now in the case of triple integral also similar sort of things is true. Now, this time what will happen? I have one variable extra. So, that means I have a function like f is a map from, say if I assume that say a to b cross c to d or say e to f subset of R3 to R. Then what will be the notion of iterated integral? Same thing, you have x variable, y variable, z variable, right. So, what you do? You just keep one variable fixed, so that means or two variable fixed y and z, think about is a function of single variable, then perform the integral with respect to x variable first, it will give you yz variable, then you perform the y variable first and then z variable. Or you can think about that, okay, I will keep the only one variable fixed, so that means keep the z variable, so that means you can write it, for example, if this is the case, then you can have this one, right. For example, a to b, c to d and say e to f. So, this is the corresponding interval of your integration, and then you have what, f of x, y, z, and then what you have to do, if I writing say first what dx. So, what I am doing, so that means keeping y and z variable fixed, I am integrating with respect to x variable. So, what it will give? It will give you a function of y and z, and since it is a function of y and z, then you can integrate dy dz, that means the double integral you can do, right. Double integral, that means you have a function of x, y variable and you perform the double integral. So, that means if I keep y and z fixed, I am doing integration with respect to x variable, okay, then it will give you a function of y and z, and suppose that function of y and z is again integrable with respect to y and z, that means you compute the double integral. So, that is one of the iterated integral. Or you can think about, like this is another way you can think about iterated integral. For example, I can say that, okay, a to b, c to d, e to f, f of x, y, z, okay, then you have to perform say dx. So, what is this? So, that means keep y and z fixed, integrate with respect to x variable, so it will give you function of y and z. Then keep y is fixed, think about is a function, or keep z is fixed, think about is a function of y variable, then perform with respect to y, and perform the integral with respect to variable y, and then it will give you a function of z, finally you integrate with respect to z. This is another iterated integral. So, therefore, you can have many ways, like, so since I have a functions of 3 variable x, y, z, so what you do, you keep either one variable or two variable fixed, think about is a function of single variable, perform the integration, then it will give you something, then again keep some variable fixed, think about as a function of one variable, then perform the integral with respect to that variable, and finally this one. So, that is the way you will have all the iterated integrals. But Fubini's theorem, what it says is that if my function is continuous, then my function is triple integrable and all the iterated integral exists. That means it does not matter which order you are doing. Either you are keeping yz fixed, doing with respect to x, and then perform the double integral with respect to yz variable, that will same as keeping y variable or x variable fixed, perform the integration with respect to z variable, it will give you function of x and y, and then perform the double integral, these are also same. And similarly, you keep the yz variable fixed, perform the integral with respect to x variable, it will give you function of y and z, and perform the double integral with respect to yz variable. So, whatever direction you can do, all directions iterated integral will exist, provided I am starting with my function is continuous. So, all iterated integral will exist, they are all equal and they exactly equal to the value of the triple integral, that exactly I have written. So, Fubini's theorem holds, that is the iterated integrals exist and are equal to this triple integral. Now, iterated integral, in many iterated integral will exist, depending upon that which variable you are keeping fixed first and with respect to which variable you are performing the integrations. Okay. So, there are many ways, either you keep two variable fixed, think about as a function of single variable and perform the Riemann integration, or you may keep one variable first fixed or each variable fixed and think about as a function of two variable and make the double integral. So, there are two ways, right. So, that means again I am just repeating the similar kind of things. So, like for example, I have this one a to b, c to d and e to f, f of x, y, z, and suppose what first, so this is I am saying that keep two variable fixed, that means y and z both are fixed, okay. Then you perform the integral with respect to x variable, okay. Then this total things will give you a function of y and z, some function of y and z, and then you perform the double integral, that is another iterated integral. Else, now the new functions you will get f of y z, so that means what we will have. So, if I have performed this one, then you will have a to b, then c to d capital f y z and dy dz, right. Then again what you do, you can keep y variable fixed, okay, think about as a function of z variable. So, therefore, it perform the integration with respect to z variable and then perform the with respect to y variable. Or you can say that, okay, I am keeping z is fixed, think about f of y goes to f of y z, because z is fixed, y goes to capital f of y comma z, it is a function of y variable. So, perform the y integration fixed, or perform the y integration first, then you will have a function of z and then perform the integration with respect to z variable. Okay. So, all possible iterated integral you will have. So, first you can fix two variable, think about is a function of single variable, perform the integrations, and the 2 variable functions you will get, then perform the double integral. Or instead of performing the double integral, in that 2 variable functions, again you can keep 1 variable fixed, think about as a function of single variable, and perform the with respect to another variable first, and then finally the last one. So these are all possible iterated integral, you can think about it. But the point is that if my function is continuous, that means it's a very nice function, then the triple integral exists, and the value of the triple integral is exactly equal to all the iterated integrals. All the iterated integrals first of all exist, and they are all equal. So therefore, that will give you a method to calculate the given functions what is the triple integral. Okay. So that means if I say that okay, calculate the triple integral of these functions, what will you do? So this depending on the functions, like, or of course or the domain, you have to be careful which domain. Okay. So depending on the domain and the functions, you can keep or you can have to integrate with respect to which variable first, keeping other 2 fixed. That's how if you proceed, if you perform all those iterated integrals, you will get the value of the what is called triple integral. In fact, next slides I will talk about couple of nice domains. There you will see if I have functions or looking at the domain, you will see which variable I have to integrate first and which variable I have to integrate second and third, and that will give you the value of the triple integral, provided the functions should be continuous. That is the first step. So that is why I am saying Fubini's theorem. Let's see, if f is continuous, if my function is continuous, then the value of the triple integral I can calculate in terms of iterated integral depending on the domain. Couple of domains I will talk about, that if you perform in this way, then you will calculate your value of the triple integral. But the point is that Fubini's theorem ensures you the value of the triple integral is exactly equal to value of all the iterated integral. Means all the iterated integral exist, they are equal, and their value is exactly equal to the value of the triple integral, provided my function is continuous. Okay, couple of nice domain I will talk, then you will see that exact the applications of Fubini's theorem. So I think it is clear what is Fubini's theorem. So just it is like the kind of similar sort of things what you have seen, that you have seen already in the context of double integrable. Then if my function is continuous, suppose you have a functions say from some bounded domain, function is continuous on R2 to R, then the function is Riemann double integrable or it is double integral exist, and not only that, all the iterated integral exists, and all the iterated integral they are equal, and that is equal to the value of the double integral. That was the statement of Fubini's theorem in functions from R2 to R, some domain of R2 to R. Similar sort of theorem is also true in the context of triple integral. That means if I have a functions, continuous function on some bounded domain, subset of R3 to R, same thing. Function, if I starting with a continuous functions, it is triple integrable or Riemann double integrable exist. Not only that, all the iterated integral exists depending upon which variable you are keeping first and with respect to which variable you are performing integral. So whatever directions or whatever order you are performing the integral, all the integral will exist, and it will give you the value, all the values are equal, and it will exactly equal to the value of the triple integral. In other words, the Fubini's theorem will give you a method to calculate the triple integral. I will discuss couple of domains and you will see. Okay. So this is the one. So first one is that triple integral of f over simple solid region G. Let's see what is that region actually, then it will be clear. What is that? Okay. So let G be a bounded region in R3. So I am putting a definition here. So I am saying that a region, the region G is said to be ZY simple. Okay, I will talk about the what is the. So I am saying that if the domain G satisfies these are the these properties, then I am saying that this is ZY simple. Okay, what are the properties? If the following 2 conditions hold. First condition is what? Let D be the projection of G in the xy plane. Okay, so that means I have a domain G which is in R3, then I am taking the projection into the xy plane. That means I am keeping z is equal to 0. It will give you something in the xy plane. If I start with a domain G and if I take the projections into the xy plane, what I demand is that D must be a y simple or vertically simple region in the xy plane. So that is the first condition. I am starting with a domain G which is a subset of R3. I am saying it is ZY simple. If I take the projections of my domain G in R3 in the xy plane, I will have some domain in the xy plane, let it be D, and if that D is y simple or vertically simple. I have explained when I talked about double integral that what is vertically simple domain. That means vertically simple domain means what? You have a 2 variable, of course I am talking about in the xy plane, x is fixed A to B, y varies from not from C to D, some constant to some constant, rather C varies from one curve, one function of x to another function of x. That is called vertically simple. Okay. So, vertically simple means x is fixed, it varies from a to b, some fixed number, whereas your variable y, which should varies from, I think, some function, say f1x to f2x. If you remember, that kind of things are there. If your domain in the xy plane satisfies this kind of properties, then you say that it is actually a vertically simple or y simple domain. So, I need that kind of thing. So, that means I am starting with the domain G. If I take the projection on the xy plane, the domain I am getting in the xy plane, it is nothing but vertically simple. On top of that, there is another condition, which is that there must exist two continuous functions in two variables. Okay, here I am talking about two variables, function of xy, and I have a function, another function u2 of xy, such that u1 of xy, which is strictly less than u2 of xy, these are continuous functions. For every xy in D, I am just excluding the boundary of my D, so that its condition should be satisfied, and G looks like this. So, G is of the form xyz, which is a point in R3, such that if I take the projection, it should be in the domain D, that is the projection of my G in the xy plane, which satisfies z coordinate. That is very important. Z coordinate should satisfy, that means z greater or equal to u1 of xy and is lesser or equal to u2 of xy, like in the what is called vertically simple domain. X is fixed, but y varies from one function of x to another function of x. So, similar kind of things. Here I have a restriction on z. Z should vary from one continuous function u1 of xy to u2 of xy, while u1, u2 are continuous functions on my domain D in the xy plane, which is the projections of my domain G in R3. Okay, and it satisfies u1 of xy, u strictly less than u2 of xy, and both of them are continuous functions. So, if I have a domain G in R3, if it satisfies these two properties, then I am saying it is zy simple. Then you might ask, okay, so this is the zy simple. Is there any kind of domain which is xy simple, or say yz simple, or say yx simple, or say xz simple, or zx simple? Yes. So, this is similar way. Like zy simple, you can also define, you see, analogous versions of like zx simple, yz simple, yx simple, xz simple, all kind of domains you can define. So, but you have to be careful which variable you have to varies from function of two variable to function of one variable, and which variable keep fixed. So, depending on that, you have to have the all the yz simple or zy simple, xy simple, yx simple, all sort of domains you can define. But I hope this is clear. So, that means a domain in R3, I am saying it is zy simple. Look at actually the, you can, from this zy simple you can guess. So, if I write like zy simple, that means the variable z, first of all, it should varies from function of xy to function of xy. So, that is the kind of association you can remember it. Okay. And what is missing here? It is missing here actually x variable, right. So, that means at the end you will see your x actually varies from, see what I am saying, that it is what, D must be a y simple or like vertically simple. What is the vertical simple domain? Vertical simple domain means x is fixed, that means x should vary from a to b, and y should vary from function of x to function of another function of x. So, that means if I write zy simple, that means the variable x is missing, then it somehow indicates, that means the x should vary from one constant a to some another constant b, that is first one. Zy simple, the first variable z, which varies from some function of xy to another function of xy, and what will happen in the y variable, since it is vertically simple, y should varies from some function of x to some function of x. So, that is how it is. Now, if that is the case, or if I have a region G in R3 which has two properties, that means if I take the projections of my domain G in R3 in the xy plane, it becomes a domain, it will give you some domain in the xy plane, and I demand that it should be vertically simple, that means x should varies from some fixed number a to b, whereas y varies from some function of x to some function of x. That is one. Number two is that if I have two functions, two nice functions, a continuous function u1 and u2, they satisfies that u1 is strictly less than u2, and for all xy d I am taking out the boundary point or except the boundary point, your G looks like all those x, y, z, where z varies from u1 to u2. Okay. So, that means if I have a zy simple domain, then you have all the things like, so that means your z varies from u1 to u2. If I take the projections in the xy plane, it will be vertically simple, that means y varies from some function of x to some function of x, and x varies from fixed a to b. Now you can see if I have a domain which is zy simple, and suppose if my function is what is called continuous functions, that means triple integral exists, all the iterated integral exists, and then you can guess which order I have to perform the integral. That exactly I have written. So that is region is zy simple if and only if it can be served as the region of integration for a triple integral with order. That is very important, with order. First you have to perform with z. Okay, that means you will have, say, I am starting with some rectangular cube region. Okay, so that means a to b, c to d, and say e to f, f of a, or sorry, I think I should not write. So this is okay. So that means suppose I am having a function f which is continuous functions, that means triple integral exists, and say then all the iterated integral exist, and then Fubini's theorem guarantees you that yes, value of the triple integral is same as the value of the iterated integral. Now since I am in zy simple, it tells you that which order you have to perform the integration, because if I have a triple what is called this zy simple domain, your z varies from u1x to u2x. So that means you have to first perform your what is called z integral. That means you have an integration, say u1xy to u2xy, you have a say function f of xyz, then you have to perform first dz integral. If I perform dz integral, it will give you some function of xy, right? Once I finish the integration with respect to z variable, then I am coming down to the xy plane. Now xy plane, what sort of domain I have? I have a vertically simple. That means y varies from some function of x to some function of x, f1 to f2, x varies from a to b. That means then next what I have to do? I have to perform the integration with respect to y variable. Now it will give you a function of what? It will give you a function of xy variable. So that means now first then I have to integrate, say, from what is called f1x to f2x. Okay, same integrand is there, so I have to put a bracket, and then you have to perform the integral with respect to y. So keeping x fixed, you have to perform the integral of y. So that means this is a function of xy, and this is a function of what? If I perform the integration with respect to y, this will give you a function of some x, and at the end you have to perform the integration like a to b dx. So that is the order you have to maintain. So if I am in zy simple domain, since z varies from u1 xy to u2 xy, so you have to perform the z integral first. That is number one. Number two, once you done the z integral, that means you are a function, the functions you are getting after integrating with respect to z variable, function of xy. That means you are in the xy plane, and the domain, the projection I am getting, it is of the form what is called vertically simple. That means y varies from f1x to f2x. So that means then you have to perform with respect to y variable with limiting, with lower limit f1x, upper limit f2x. Then it will give you a function of x, and then you perform the x variable integration. That means lower limit is a, upper limit is b, because x varies from a to b. I hope this is clear. So zy simple means you have to first perform the z integral with lower limit u1 xy, upper limit u2 xy given from the domain. Then you have to perform with respect to the y integral, again lower limit f1 x, upper limit f2 x, since y varies from f1x to f2x, and finally you have to perform the integral with respect to x variable. That means x from a to x from b. Okay. So that means now I will talk about that. I will give some one example, then it will be more clear. So okay, so this is called zy simple. Similarly, you have all the like zx simple, yz simple, yx simple, xz simple, xy simple, all sort of domains you can talk about. Maybe I will talk about one or two more domain, then it will be more clear. But parallelly, similar sort of things depending. So you have to just kind of play with the corresponding variable, which of the variable you are keeping fixed, you are taking the projections, whether it is vertically simple, horizontally simple, this kind of things. So zy simple, if you understand one simple domain, zy simple domain clearly, analogously you can define all zx simple, yz simple, yx simple, xz simple, xy simple domain and perform the integration accordingly. Okay. For zy simple means what? You have to perform the integration with respect to z variable first, then you have to perform the integration with respect to y variable first, and finally you have to xy variable. So if I have a zx simple, that means you have to perform the integration with respect to z variable first, then you have to perform the integration with respect to x variable first, and at the end you have to perform the integration with respect to y variable. Similarly, yz, yx, xz, xy. xy means what? So this simple, if I talk about this one, first you have to perform the integration with respect to x variable, then perform the integration with respect to y variable, and at the end you have to perform the integration with respect to z variable. Okay, let's see. Yeah, so that's I tried to kind of given you as a kind of pictorially what is that. So okay, what is zy simple? So in this picture, G is a solid region which is given by, look, so this is my kind of u1 xy and this is u2 xy, and I am taking the projection on the xy plane. This is the corresponding domain it will give. So this is my G, so all those x, y, z in R3 where z is greater or equal to u1 of xy, lesser or equal to u2 of xy, again u1, u2 are continuous functions. And if I take the projections into the xy plane, which is nothing but D, which is an xy plane, and it is a simple region. Y simple or vertically simple. And what is the vertically simple? And x should run over some fixed number a to b, and y should run over some function of x to some function of x. Look, same thing. D is given by all those xy in R2 where x is running from a to b, however y is running from v1x to v2x. Now here everything I am assuming nice that v1, v2 are continuous functions, u1, u2 are continuous functions. So this is actually the zy simple regions. Parallelly you can define what is called xy simple, yz simple, zx simple, depending upon which variable you are having that projections and corresponding y simple or x simple. Okay. Let me see what I have. Okay, so I think zy simple region is clear. So if I have a zy simple region, that means z varies from u1 xy to u2 xy, and if I take the projection onto the xy plane, that means z is equal to 0. That means the corresponding domain I am getting, it is actually vertically simple. That means x should run over a to b and y should run over some v1x to v2x. Once I have that one, then I can calculate the triple integral over this domain of some function, nice function f, by performing the z integration with respect to z variable first, then I will do the perform the integration with respect to y variable, and at the end x variable. That iterated integral if I perform, it will give you the iterated integral exists. Of course, if I assume that my function is continuous, and the value of the triple integral over this domain, if I perform the iterated integral in this direction. What directions? First you perform the integral with respect to z variable, then you perform the integral with respect to y variable, and at the end you perform the integral with respect to x variable. Okay. So let's see, this is the example I have given. Oh, this is actually Fubini's theorem. Okay, exactly whatever I just said. Fubini's theorem for triple integrals over zy simple domain. Okay, or zy simple regions. Okay, zy simple region, it's clear. Now this is the theorem. Using that theorem, you can calculate your triple integral. What I said. So this is a statement of the theorem. So let G, what sort of domain? It is the collection of all x, y, z, where x running from a to b, z running from u1 to u2, u1, u2 are continuous functions, and you see it is vertically simple, that means y running from v1 to v2. So if a domain having this kind of properties, then it is actually zy simple region. Now look, let f be a function which is continuous functions. That means my triple integral exists or Riemann Darboux integral exists, and the value of the triple integral, you see, this is exactly the order you have to follow. So first you have to perform with respect to z variable, it will give you a function of xy variable. Then you have to perform the integration with respect to y variable, it will give you a function of x, and at the end you have to perform the integration with respect to x variable. So this is the iterated integral, right? So first you are doing integration with respect to z variable, keeping x and y fixed. Okay, then it will give you function of xy. Then you are keeping the x variable fixed, x is fixed, then you perform the y integrable, it will give you a function of x, and finally you are performing the integral with respect to x variable. And why you are doing this kind of order? Because in that case you see the limit, the lower limit and upper limit of the integral, it's actually a function of x and y. So if you do the other way, you will face some difficulties. So since z varies from not like some constant c to d, rather it varies from some function of xy to some function of xy. So this will kind of forces you to say that yes, you perform the z integral first, or integral with respect to z variable first, because it varies, your lower limit and upper limit varies from some function of xy to some function of xy. So therefore I am performing for z integral first, keeping x and y fixed. So it will give you function of xy, and again since y again varies from function of x to function of x, that means it somehow indicates that after that, once I have a function of x and y, by performing the integral with respect to z variable, you have to perform the integration with respect to y variable, because y varies from one function of x to, or lower limit is v1x to v2x, then it will give you function of x. And now if you perform the integral at the end with respect to x variable. Now x varies from some a to b, then it will give you some number. So therefore the triple integral will have the kind of appropriate meaning. So that means if I have zy simple region, okay, zy simple region, you know the variable, how the variable varies. X varies from fixed a to b, y varies from function of x to function of x, and z varies from function of xy to function of xy. And if I assume that my function is continuous, that means triple integral exists, all the iterated integral exist, and if I perform the iterated integral in this order, that means I have to perform first integration with respect to z variable, keeping xy variable fixed, it will give you a function of xy. Then I will perform the integration with respect to y variable second, keeping x variable fixed, and at the end I will perform the integration with respect to x variable. If I perform the integration in this order, by keep in mind that when I will perform the integration with respect to z variable, my lower limit should be u1 xy to u2 xy, because z running from u1x to u2x. That is very important. And then when I will perform the integration with respect to y variable, keeping x variable fixed, then you have to be careful, the lower limit y should be v1 of x and upper limit should be v2x. That means because y varies from v1x to v2x. Okay? And at the end, when I will have the only function of x, you have to just perform the integration with respect to x variable, lower limit a, upper limit b. So if I perform the integration in this order, by keeping in mind that when I perform the integration with respect to z variable, lower limit is u1 xy and upper limit is u2 xy. When I will perform the integration with respect to y variable, lower limit will be v1x, upper limit will be v2x, and at the end when I will perform the integration with respect to x variable, it should be a to b, since x is running from a to b. If I perform the integration in this order, it will give you the value of the triple integral. So that's the kind of formula. Fubini's theorem says that if I have a function f which is continuous, and if your domain is zy simple, all the iterated integral, triple integral exists, their value will be same, and hence I can evaluate my triple integral by performing the iterated integral in this order, first with respect to z, then with respect to y, and then with respect to x. Okay. You see, I have written analogous statements hold for each of the other 5 simple regions. Okay, I will talk about 1 or 2, but other simple region now you can guess at least how to adjust. So depending on which zy simple or yz simple or xy simple you are giving that domain, and then you can do that. Okay, I think I just calculate one example and then I will stop here. Okay, so what is it? Look, I have a functions f of xyz, which is xy plus 2z, which is a continuous functions. Very nice. All triple integral, iterated integral will exist, so you do not worry about that. Okay, and their value of the iterated integral is same as the value of the triple integral. Now look at the domain, that is very important. So it is given that all those x, y, z in R3, look, so z varies from 0 to xy. That means I can think about this as a function of x comma y. That means what is your e1 of xy? If I just relate it with my earlier slide, this is 0, and what is u2 of xy? This is x times y. This is a continuous function, this is a continuous function. So z varies from this. Okay. Then what is given? Y varies from 0 to x. That means earlier what will happen? So v1x, v2x, right? What is v1? What is v2? This is v1 of x, which is 0, and v2 of x, which is x. This is also continuous functions, and x varies from 0 to 1. So therefore my domain, which is of yz simple, right? So that's exactly I have written. So this is of the, oh sorry, not yz, zy simple, yes. So this is actually what is called zy simple domain. Function is continuous functions. So therefore Riemann Darboux integral or triple integral exists, all the iterated integral exist, their value will be same, and it is exactly equal to a triple integral. Now by Fubini's theorem, value of the triple integral is exactly, you have to perform the iterated integral in this order. That means you have to first perform the integration with respect to z variable, keeping the lower limit as z is equal to 0, upper limit is xy. Then perform the integration with respect to y variable, keeping that lower limit is y is equal to 0, upper limit is x as it is, and at the end you have to do the what is called x integral, x varies from 0 to 1, this is 0, this is 1. And just do that. Now function is very nice if you perform that one. Okay, so this is z, so that means this should be x, keeping xy, of course first one you have to perform the z variable with respect to z variable, that means keep x and y fixed. So then if I x and y fixed, so that means it is xyz, this will be z square by 2, that means z square, 2 get cancelled. So what will be a limit? Z from 0 to xy. So it will give you actually z is equal to xy, that means x square y square plus xy whole square, again x square y square, that means it will give you, okay. So that will give you 1 x square y square, and this will give you 1 x square y square, because z is equal to 0, this will give you 0, this will give you 0. So that means the first one, that's upper limit, it will give you x square y square plus x square y square, that means 2 times x square y square. Then perform the integral with respect to y variable, keeping x fixed, that means you have to perform the integration of y square. So that means it is y cube by 3, that means 2 by 3 will be there, then you will have x5, perform the integration 0 to x. Okay, so lower limit will contribute nothing, so we will only have the upper limit x, so it should be 2x to the power 5 by 3, and then it will give you the value 1 by 9. Okay. So now I think it is clear, that means if I have a zy simple domain and if my function is continuous, by Fubini's theorem your value of the triple integral, if I perform this what is called iterated integral, and also which order you have to maintain, it is clear from which domain you are working on. Since I am in zy simple, that means you have to first perform the integral with respect to z variable, lower limit should be z varies from 0 to xy, that means 0 to xy. Keeping xy fixed, perform the z integral first. Then you will have a function of x and y, then you have to perform the with respect to y variable, because your limit y, lower limit should be 0 and upper limit is a function of x. You perform the integral with respect to y variable, keeping x is fixed, and at the end you perform the x integral with limit x from 0 to 1, that is given. Okay. So I think I should stop here. So this is only for zy simple domain. I have explained what is the definition of zy simple domain. Then I stated a theorem which is nothing but the Fubini's theorem. If I have a zy simple domain, then your triple integral exists, which is exactly equal to the value of the iterated integrals. Depending on the domain, I said that okay, if you perform the iterated integral in this order, you can calculate that iterated integral, and that is exactly equal to the value of the triple integral. Okay. So I think I should stop here. Okay. So next time I will to talk about what is called another domain, that is called yz simple. I think not all xy, yz, xz, zx, all simple domain I will talk about. Maybe one more simple domain I will talk about. Again I will talk about Fubini's theorem, then you will have at least better idea. So parallel or other domain you can just do it parallelly, depending on the domain you can guess, okay, that means which domain it is and in which order I have to perform the integration, provided my function is given continuous. Okay. I think in my next lecture I will talk about that. I think I should stop. Thank you.